So solvent and solvent choice are really critical in determining nucleophilicity. For one, really hard atoms like fluoride, for instance, then are actually decent bases themselves. F minus is a hard atom, and so it's interested in this infinitely hard atom as well, the nucleus of a hydrogen or a proton. Iodine, on the other hand, is a big clumsy oaf. Not big and clumsy oaf, that's mean. Iodide is an indifferent, large, iodine is special. Iodine is large, it has very limited interest in H, and as a consequence, it doesn't really have a particularly strong solvent effect. At least solvent effects in the context of protic solvents like water. Those don't really affect iodide. Fluoride, on the other hand, is really hydrated when it goes into water. Fluoride likes to pull the hydrogens off of water. It's like a cruel child that pulls the wings off of flies. Fluoride enjoys being in water to a sadistic extent. Iodide, largely indifferent to it. And that brings up an important point about water and other protic solvents, methanol, ethanol, all those sorts of things. If you're going to have a nucleophile, right? So if you're going to have a nucleophile that has a lone pair, it's going to go for the water, right? You don't want to have a nucleophile around a bunch of water because, as much as I said, nucleophilicity and basicity are just close enough to be, are related. Nucleophilicity and basicity are related enough for free protons from water and other media to actually cause a problem. So you probably don't want these really polar wet solvents that have water and acidic protons around your nucleophiles. Because granted, iodide is not particularly interested in protons. That's not to say it can't and won't slow down in their presence. Just because it's not interested in them doesn't mean that it's uninhibited by them. So solvent effects play a pretty big role in determining the nucleophilicity as well. Another important thing to consider is the actual geometry of the transition state structure. So the transition state structure is an important parameter in the whether or not this reaction proceeds at all, right? So I've drawn this transition state structure a couple of times, and it probably should be drawn more with like dashed bonds here to indicate that chloride is leaving and that OH is attacking. And I've drawn it like this. And this transition state structure is a trigonal bipyramidal molecular geometry. Okay, so you can see that there is a pyramid that is associated here, and it goes off in the back here, it comes out in the front here, and then that connects here. And then you have the top and the bottom of the pyramid that's here, and that forms some geometry back here, and down here, and then here, and goes there, and that forms there. So that is a pretty cramped geometry. If this transition state structure becomes too large, say for instance this green dot that I've included, in fact I'm going to just clean up a bit here just to get rid of one side. If my green dot happens to be particularly huge, like say this big, say it's a benzene ring or a cyclohexane ring, you know, that's going to be a huge green dot, and that's not going to leave a whole lot of room for this blue dot to form. And this blue dot over here, right? There's a geometric constraint that's associated with this, and in order to really form this really cramped structure, if your reactive compound is too big or your nucleophile is too big, you just won't end up with a reaction at all, right? You can imagine, instead of showing a hydroxide group, I sent in this. All right, suddenly we have now a blue dot that is considerably larger, and that blue dot is like, ow, on this green dot, okay? It suddenly becomes much harder for this transition state to even form. And so an important parameter of the SN2, in fact, it's extremely sensitive to sterics of the nucleophile. So if a nucleophile is very large, this reaction pathway is just not going to really happen. In order for this SN2 chemistry to occur, we need to have a couple of things that are going to be true. All right, and this is just, let's get the nucleophile. For the nucleophile, we need it to be small. All right, it needs to be squishy. Really a combination of squishy and electronegative. So some combination of squishy and electronegative. And you need to do it in a solvent without protons. All right, so a protic solvent's not going to really be quite helpful. Now that's just for the nucleophile. We also have some constraints on this structure right here, the electrophile. All right, now obviously the electrophile needs to have be relatively small. It needs to be dipolarized. It needs to be able to accept 2 electronegativity. But what about the things it's leaving, right? It's a substitution reaction. So what about the thing it's substituting? That chloride in that particular case. What makes that a good leaving group? Well, good leaving groups are very much like bases. They should be a terrible base, all right? The worse base it is, the better, because a really good base, all right, is going to be summarization over here, because I'm going to go back to this in a second. Bring that down here, and this is our nucleophile. We'll call it a nucleophile wish list. What's on our electrophile wish list? All right. Oh, for an SN2 reaction. Keeping in mind this is now strictly SN2. Again, small. Or something that doesn't have a lot of these spinach coming off of here. You want something relatively small electrophile. You also want a big dipole. That's important, okay? Solvent effects are the same. Obviously, if you have a bad solvent, you want a solvent that's going to not particularly stabilize that dipole. So if the solvent itself has a great dipole, it's going to align itself with the electrophile. You kind of want a solvent that doesn't have a dipole at all. So a less polar solvent is really the preferred one, but we'll get a little bit more into solvent effects down the road. Really, I think an electrophile, if you really want a great electrophile, you need a great leaving group. I didn't write the word great. That's an important part of the whole equation. You need a great leaving group. Wow, I could just fit the whole thing in there. You need a great leaving group, all right? And I've not really defined what a great leaving group is. So what exactly is a good leaving group? Well, it's leaving, so when it pops off, it ought to be stable. It ought to come off and just be quite happy with itself. It ought to be happy being negatively charged or having a lone pair or something like that. And it really should be something that doesn't mind being a base with negative charges, that doesn't want to attack or deprotonate anything. It really should just be a really bad base. So a good leaving group is a bad base. And you'll note that I didn't say it's a bad nucleophile, because you can actually have a good leaving group that's a good nucleophile. It just has to be a bad base. Because what is a bad base after all? A bad base is something that is totally happy with being negatively charged. It doesn't want anything more out of life. It is perfectly happy with the way it is, right? So you have to remember that you have a nucleophile and some sort of negative charge. It's going to be attacking something that's polarized. It's that polarized thing is going to pop off, and you're going to end up with the substituted carbon, and then this thing right here could dangerously, if it's a good nucleophile, that's possible, could go the other way and kick off your nucleophile. So in order to prevent that, what you really need this thing to be is totally, more or less, inert. Now, anything that you can put down here that is a bad base equals good leaving group. So pretty much what's out, all right? So, all right, hydroxide, bad leaving group. Hydroxide, that's out. In fact, any oxide, any alkoxide is out. NH2 that's definitely out. In fact, I would even say NH2, although that's a pretty decent base, it's not a good leaving group. It really just isn't. You really shouldn't have that. But let's just say these should never be used. Bad leaving groups should never be used. All right, and of course there are exceptions where they will be used, but you will never cover them in Organic Chemistry 1. So let's just say you will never kick something off as OH minus or any sort of N minus or anything like that. Now, I did say that iodide is a pretty good leaving group, and also it is a pretty good nucleophile. As it turns out, all the halides are pretty good leaving groups. In fact, iodide is unusual. And we'll discuss these two particular ones because this goes with the softness versus basicity argument, right? There is one atom that I do want to bring to your attention that does break some rules, so let's cover it a bit more in detail. So fluoride is an exception. Fluoride is a terrible leaving group. It is not a particularly great base, although it's certainly more basic than I-. It's not a good nucleophile either. Overall, fluoride is just an exception. F- is a horrible, that's not, let me just write that, horrible leaving group. It really, you would just never write it. Fluoride is not going to pop off easily. It just holds on to the carbon. It just holds on to carbon way too strongly. A good leaving group is in fact promoted by being squishier, right? Something that when it pops off, it doesn't immediately freak out, like, what am I going to do with these electrons? A good squishy atom can just slosh them around all over the place. Fluoride is at that corner of the periodic table where essentially it has very unique and terrible properties that, terrible and wonderful properties, but terrible nonetheless. So in the context of leaving groups, what you end up with, the best leaving groups being electron withdrawing that can polarize the carbon atom, that are stable but not a strong base when they leave, and that they're polarizable, and that it helps stabilize the transition state. All right, so let's summarize SN2 chemistry. In fact, SN2 chemistry can be summarized really with that energy chart that I illustrated up there. SN2 chemistry is a bimolecular reaction. It has a single transition state. And that transition state geometry dictates all kinds of things, in particular how big the nucleophile can be and how big the leaving group should be. And you should come away from this lecture understanding a couple of terms very well. You should know what the nucleophile is. You should know what the electrophile is. You should know what a leaving group is. You should know, at least pretty well, what the transition state structure is of an SN2 reaction, and the things that limit it, including the nucleophile and the leaving group. The things that limit the reactive energy, the energy of activation. How nucleophilic strength is important there, as well as leaving group. You should also, of course, remember that this geometry means that there is a change in stereochemistry, at least a very likely change in stereochemistry, with them often flipping from R and S because nucleophiles attack from the backside of the reaction. With those things in mind, and if you have a good understanding of those, you're ready to move on to the next one, which is SN1 chemistry, which undergoes an intermediate structure and two transition states on its way to a product.